需要给它要匹配点什么样的一个就等于说有那些 condition 的时候就 realize otherwise 是个 abstract 的一个
其实是拿它来本也好。
Were you here?
Still working on the current sheet?
Yeah, so I'm talking about current sheet. I'm trying to make the process different.
Okay, we'll have our second talk in the morning. Our speaker is Lan-Hsuan Huang from the University of Mathematics. Lan-Hsuan will speak on the constraint manifold with a dominant energy condition.
Thank you for having me here. It's a great pleasure to visit the center for the first time. Can you hear me?
Not much.
No, not much. Okay. But can I adjust? Okay, let me just try to speak loudly. So, the goal of the research project is try to understand the local geometry of a moduli space of initial data set. Right, so we want to study paths of the moduli space of initial collection of initial data sets on, say, a fixed topological manifold. And we want initial data set to satisfy the dominant energy condition. So we're interested in local paths. So this is like a given initial data set, what kind of paths you can find to promote some quantity you have in mind. So we're interested in particular two cases. We're interested in the path from a given initial data set to a nearby one that can promote the dominant energy condition. So one thing we have is from weak inequality to strict inequality. So think about in the more space-time thing that will perturb a node vector from the time-like vector. And also, we're interested in the result. We'll have the good application in mind is to promote from almost dominant edge condition to dominant edge condition, right? So you perturb from something which may lie outside the light cone, but you want to perturb inside the light cone. Our guiding principle is the fundamental observation of Friction and Professor Yao. So they look at the Riemannian case for manifold with positive scalar curvature. And if there is a stable minima hypersurface inside, and then the induced scalar curvature on a stable minima surface will also on average has positive scalar curvature. So this observation revolutionized the field of our understanding toward scalar curvature, because we know only really before their result, if we have scalar curvature on the manifold, what we can say about it. We really only know in 2 dimensions, okay, by Gauss formation. And the result tells you, if you know better, like the low dimensional case, you can actually know what happened in the bigger dimension. And then, but that tells you some topological restriction or some geometry of the big manifold N. So the question now is whether you can promote the scalar curvature up, right? So it's already highlighted in Justin's talk. So it's not always be doable. There is some abstraction. But we are working on with the full constraint map. Okay, and outline of the talk is I will review some of the results for the Einstein constraint map and see how that helps us to promote the dominant energy condition in the vacuum case. So we'll first talk about manifolds without boundary. and then talk about abstraction. And for asymptotic flat manifolds, because now we are working with unbounded things, so somehow you can push things toward infinity. And so we have two different cases if we want to promote dominant edge condition. So whether we allow global deformation, which in a sense you want to perturb anything, you want on the manifolds like everywhere. Or localized deformation, you want to only promote the dominant edge condition within contact set without change everything outside. And then we'll talk about some of the recent work with respect to the dominant energy condition, general, like maybe non-vacuum. And for dominant energy condition, how can we promote dominant energy condition? So we'll talk about some issues happen different from the vacuum case, and like motivate us to use modified operator. And there's global deformation results. That's a joint work with Mikhail Egmai, Dan Lee, and Rikshan a few years back. That's in our project to prove the space-time positive mass theorem. And one of these global deformation results is an analytic ingredient in lab proof, which let me show you the statement. So the theorem says if we have an asymptotic flat manifold with the dominant energy condition, then we can find a path which really bring up the dominant energy condition. So be careful though, because you can do some simple scaling just to scale pi, for example, because there is some discrepancy between the scaling of matrix and pi in the scalar the constraint equation. You can just simple scale pi to bring up the dominant energy condition. But this is not exactly we need in our for application, because we need this gap. So in other words, the ratio of these two quantities has to remain quite positive even toward infinity. And that will allow us to do some cutoff trick and then still keep the dominant energy condition. And here, one thing is this is global deformation, so there is no abstraction. So this works for any initial data set. Even for flat, you can always bring up the dominant energy condition. More recent work is for localized deformation, and that's a joint work with Justin Covino. And we find out some sufficient condition enable you to promote the dominant energy condition only inside a compact set. And we have a gluing application in mind. And what our gluing application says, if we have a asymptotic manifold with, again, dominant energy condition, then we can find a matrix with a dominant energy condition such that the matrix coincides with the given one on the compact set, and then somehow you can transit it towards some model family, like a Kerr or even Kerr-Newman family. So over this interpolating region, we can keep the dominant energy condition. And in fact, we can probably perturb the dominant energy even a bit larger to make sure the Kerr or Kerr-Newman family we glue at infinity has strictly larger mass. The mass is here will be E squared minus P squared if you have a momentum. And we are talking about really bringing up the ADM mass. Okay. So that relies on the local deformation because you can just simply interpolate these two data. But over the annulus region, the dominant edge condition fails, right? So here the application is we can bring up dominant edge condition only in this annulus. So here is a constraint map. Given initial data set, which G is a Riemannian matrix, pi is a symmetric to tensor, and some people call that momentum tensor, which is some deformation equivalent to the second fundamental form, but it's just easier to work analytically. So we can write down the constraint equation from the Einstein constraint equation, Einstein field equation on this induced quantity G and pi. That becomes the scalar curvature and some quantity including pi. And that's the first set of equation. And then for the second one, which is we'll have a symmetric to tensor, we can define divergence. So this is a vector equation. constraint map is a map sending initial data g and pi to those mu and j for the current and mass and current density coming from the matter field. So the dominant energy condition says the matter field, the stress energy tensor measured by a normal observer has to be either null or time-like, has some positivity of the matter field. And in terms of initial data set level, Larry down as a condition mu has greater equal to j. Remember, j is a vector field, right? So this is the null of j, which becomes a scalar field on the manifold. So in the case with pi 0, now recover to the Riemannian case where you only have scalar curvature, and this condition becomes non-negative scalar curvature. So for a closed manifold, so as pointed out in Justice's talk, there's this nice splitting theorem for functions. So the function space can be split into the range of a differential operator and the kernel of a joint operator with injective symbol. So in our case, we are looking at a constraint map. And constraint map is a smooth map. From initial data set to mu and j, this is a smooth map. So you can take a differential. And then both the differential and the joint has injective symbol, so we can apply the splitting theorem. That's what has been done in Fisher-Marston work. And now they locate the condition if the kernel of a joint is trivial, then that implies the range of the linearization is surjective, right? It's the whole space. And then by local surjectivity theorem, that tells you the nonlinear map is also locally surjective. So we're asking about like promoting dominant energy condition, but somehow we rely on a stronger result like surjectivity, right? Although we are looking just in particular paths which bring up the quantity, but somehow you relies on we know more about that was the image of the map. And for asymptotic flat manifolds, now we have unbounded region, and the surjectivity of this map really depends on what function space on the consideration. So we have global deformation, which think about you really are able to change everything, every point on the manifold. But you also want to keep asymptotically flat condition, right? So you're looking at the constraint map still defined on the class of asymptotically flat matrix, so you require some falloff rate. But it can be non-zero, goes to zero sufficiently fast. And in that case, there's no obstruction. And then for localized deformation, you are looking at the constraint map on the space of initial data set, which somehow coincide with your given one outside compact set near infinity. In that case, the adjoining operator somehow relate better to whether the linearization is surjective or not, right? Because it's not only the formal L2 adjoining operator, somehow it's really because you are looking at compactly supported guy, is really the L2 adjoining operator, the D star. So there are two different cases. For the global deformation, if we are working on the right space with some appropriate decay rate, this linearization is surjective, and that's the result of Choquet-Bruhat, Fisher-Marston in the maximal case, and also by Omohata in more general case. And then Kovino-Shen show that it actually tells you this nonlinear map is surjective, because we're working with some kind of subtle function space, right? So it does not follow from local surjectivity theory directly for the nonlinear map. But somehow Kovino-Shen, they using a very nice argument to show this map is also locally surjective. And even more, they can decompose the solution into elliptic part and then plus some smooth compact perturbation. So they impose the ansatz of the deformed guy parameterized by u, scalar function, and x, a vector field, plus some compactly supported tensors. And then it's more somehow analogous to the scalar curvature case, right? You do conformal change to deform the matrix. But there's also some mysterious vector field there. And these two parts, u and x, leads to so-called harmonic asymptotics, which already has very application application for example, in the proof of space-time positive mass theorem. So somehow it's still kind of mysterious, like what does that mean, these particular answers? Because it doesn't seem to be realized by some space-time matrix, but it really just works so well mathematically. Okay, and also it's nice to decompose these two parts because then we can apply elliptic estimate, right? Here it's only in the weak directive sense, but once you have elliptic thing, if you know original matrix has some good regularity, that tells you the solution also has some good regularity. Questions so far?
Yeah, I have a question. What's the contribution of Weig and Muraku to this problem?
So here they proved for the maximal case, right? And then here they prove the general case. This is subjective. Okay. So for localized deformation, there is abstraction. So you cannot always bring curvature up with it, or thermodynamic condition up in the compact set. But on the Guo condition, you can do that. So that's in the work of combination and crucial delay. They find out the condition very similar to the case of closed manifold. If this kernel of a joint is trivial, then this nonlinear map is also locally surjective. In the sense, like if you do compactly supported perturbation of the constraint map, that can be realized by compact supported deformation of the data. And this local deformation leads to various applications for gluing, also already demonstrated in the reminder case by Justin in his talk. And then abstraction, in this case, if the kernel is trivial, what will happen? So just look at the example for the Euclidean case. Three-dimensional Euclidean case, you can write down the joint operator in a nice way. This will just be a Euclidean Laplacian. Sorry, this G is not, it shouldn't be there. Oh, there is there, right? Yeah, it's a tensor. And then plus the Hessian of the function. N is a scalar function. And then the second component becomes the lead derivative of the matrix in the x direction. So what happens if it's 0? In the first component, you can see like if you linear function. So it'll be constant plus the coordinate function. And the second one really tells you what the symmetry of you have for the Euclidean space, right? So that get all your Killing vector field of your three-dimensional Euclidean space. And what's very intriguing relation I find out is it actually Moncrief identified this kernel element, not only in the spatial case of Euclidean space, but it's for general. If there's a kernel, actually the kernel elements one-to-one correspond to the Killing vector field of the space-time developments. But this correspondence, as far as I know, only holds for the vacuum case because they really need to use the first you have a unique development, space-time development, right? And second, they use some special property of the Einstein field equation being vacuum, so reaching flat. But this is a very intriguing relation to me to see this actually corresponds to something in space-time. So now let's see. Here on the subjectivity of the full constraint map can help to promote dominant condition already in special cases. So by subjectivity, that means if we have given mu and j, so given the data g and pi with the mu and j, and then for some small prescribing quantity, the c and v, we can find out it's realized. So we can find deformed data with log mu bar and j bar. So in those two cases, if j is 0, then we can choose v to be 0, so to make j bar to be 0. Or in that case, if it's very close to 0, then we can just prescribe v to cancel out that term. So in all those two cases, we know j bar is 0. So why do we need that? Because in a dominant energy condition, remember that's mu bar minus the known of it. But you are also measuring the matrix that's changing. So if you, in this case, somehow you just eliminate this term, and this dominant energy inequality becomes just mu plus per c, and then of course you can choose per c to be, say, positive positive to bring it up. So let me just draw some heuristic picture to see why it will work in those two cases. So think about, so although we are doing deformation everywhere on the manifold, I just say fix a point, and we look at tangent space in the space-time. And mu greater equal to j means it's inside the line cone or along the boundary of the line cone, right? So this shaded region means the area inside the line cone. So if j is 0, that means you're already inside it. No matter what kind of matrix you have, it's an open set. It's already, and also lie along the mu axis. So here I'm looking at like a 1-1 Minkowski space. So here is the time direction, this is j, and this boundary is the null vector, and this inside is the time-like vector, right? Just some simple heuristic picture. And now if we bring up the C, and then you change the matrix, so the line cone changed. It becomes smaller. But you are still do perturbation such as lie along the axis, so of course it's inside the line cone. And also for the case j is very close to 0, if it's outside line cone, so the dominant edge condition fail at that point. And then how can you bring it back? Suppose you can do subjectivity, then you bring up along the axis. So even the matrix change, the line cone become very small, but the way you do lie, you make it lie along the time axis, so it's still time-like. But for the non-vacuum case, that could be an issue if you just rely solely on the subjectivity of constraint map. So first issue is one natural idea may be to do like a local subjectivity theorem for this quantity mu minus j, right, as for the scalar curvature case. However, this operator may not be differentiable because we have a square root of j. And if you square root, remember it's only Lipschitz if the vector can be 0 at some point. So it's only Lipschitz there. So we cannot really just say take a linearization of it. It doesn't really make sense because not even differentiable, it's only Lipschitz. For the case it's differentiable, Shen Yao actually using conformal change to realize already. So we are really working at a case which is not differentiable. So j first is not 0 everywhere, and j may change its sign. And the other issue is the promoted dominant edge condition does not follow from just the subjectivity constraint map. So remember, subjectivity constraint map roughly tells you you can choose the, if here is the vector of mu and j, that tells you where you can place the vector. But also when you place a vector, the size of line cone change. So if you are in the borderline case, mu equals to null j, so that's this borderline case. And now you want to say, I want to bring it inside the line cone, I want to do this direction. So we do bring it up, but the line cone also changes. So there is some really subtle balance between the quantity you prescribe and also the deform you need to make for the matrix. And let's look at this, we just here's the picture, right? So, but let's look at more quantitatively how subtle balance between the prescribing quantity and the deform of the data you get. So instead of looking at the non-differentiable thing, just look at take a square, right? Because if this is greater than 0, that will imply the one without square also have the strict inequality. So if we do linearization of it, now it's differentiable because we get away of the square root, and we have a linear or variation of this quantity to mu delta mu, and then we have variation of the norm of the j. So one term will come out, it will be the variation of the matrix, and then the variation of the vector j. And here I make it red because that's the problematic thing. So if you prescribe constraint map, delta j and delta mu is something you can control, and delta g is the solution you get, right? But now how do you control then? You want the right hand side to be, say, positive. But how do you know control? So we do have so there are estimates between delta g, the deformed guy, and the prescribing thing, but it doesn't seem be good enough to tell us this term, say, will dominate this one, or delta mu if you choose positive to dominate this term. So there's some sort of competition between those quantities. So our idea becomes very simple, right? How about just eliminate that trouble term? So here, if we factor out the j, delta j is something we can control, we can prescribe. And we want to let it cancel out the trouble term. But you think more carefully, how can you do that? Because delta g is the solution we have from prescribing the blue term. But we want to make sense of this idea to cancel out this red term. So we let this delta j or 2 delta j to be the minus of it. And here the dot is just a tensor contraction, right? So after tensor contraction, it's really canceled out this one. And to realize our idea is we are not prescribing the constraint map. We prescribe the modified one, which incorporate the thing we like. So here we define a modified map. So that's the usual map. So here we are really, for the global deformation, we really need just work on the linearized operator level. So we have the usual linearization of the constraint map, and then we plot some extra term. So this term is really, remember, if you prescribe per C and V for this operator, and this term will add up to at V, that will be able to cancel out the thing we like when we compute the norm of J. But analytically, this is really not much different from the usual map because you just add a zeroth order term. So all the estimates go through for this modified operator, the same estimates. And so we can go through the subjectivity of this d phi and apply to this modified operator. We show that it's still subjective. And once subjective, that means we can choose some, this is linear map, right? So we can choose some large thing. So we can choose some positive enough quantity per C. So we want it positive, right? Remember, we want to bring up the dominant energy condition. And if we choose this positive enough, that will appear. So we just compute now. So once it tells the solution H and W, we look at the path in that direction, the straight line in that direction in the moduli space. And then by direct computation, so this quantity comes in. So remember, there's a t there, so the linearization becomes t times this prescribing quantity. And then originally, if we don't do this modified operator, there will be some the same order change of the matrix t there, but that cancel. And all the remaining term will have higher order. So we are looking at t very, very small, just like a small path, t very small. And so this particular fallout rate is to be able to absorb the fallout rate from other error term, the quadratic nonlinear term. Okay, so when t is sufficiently small, and you can see this term will dominate all the error term. So this is what we get. So you can see we actually get the whole path, right? So we find a direction which can bring up the dominant energy condition with some small amount. This gamma depends on epsilon. Also, epsilon, you can think about the t in my previous slide there. Depend on p. So when t is small, the gap is small, but when t is further away, the gamma becomes larger. So this application we have in our paper is we get two proofs of the space-time positive mass theorems. Here we say space-time because we're really looking at the thing with non-zero linear momentum. Right, so E greater than B to distinguish the positive energy theorem, which only say E greater than equal to P. So we have two proofs. So the first proof is extension of Shen-Yao's minima surface approach. So the highlight is very similar to the fundamental observation of Shen-Yao, which the positive scale curvature is inconsistent with the stable minima surface inside asymptotic flat manifold. And here is the observation, strict dominant energy condition is inconsistent with the stable mods. So here we need to bring up the dominant edge condition. And also the other new contribution of our paper is we find out we can show existence stable mods. Because in the minima surface approach, the stability coming from minimizing the area. But mods is not known to be variational, so we don't have a quantity to minimize it. So we have to somehow find a way, although the stability makes sense, but we have to find some way to, how do you construct, how do you find out there is a stable mods. And then once we know there is stable mods, then Galloway-Shen, they show the dominant edge condition somehow it will tell you on average the scale curvature of stable mods is also positive. And then they will, in low dimensional, like directly contradict the Gauss-Bonnet theorem. In high dimensional case, you have some reduction argument there. So that's one proof. And then the other proof is somehow make a rigorous argument of more heuristic approach is to relate the E greater equal to B theorem to the positive energy theorem, the E greater equal to 0 theorem by Boost. So the only thing missing in that heuristic argument is how do you know there is such space-time development? And one contribution here is to give an initial data set which may not be vacuum outside, we can deform by a two-step deformation to make it exact vacuum outside compact set. So first we bring up the dominant edge condition, and then we can cut it out. And the positivity of dominant edge condition will absorb the error term from cut out to be vacuum outside. So once you know it's vacuum outside, there's a boosted space-time development, and you can do boost there. Right. Okay. So now let's talk about localized deformation. So we want to promote dominant edge condition only with the compact set. So we really need to work on nonlinear map, right? The linear map is not good enough for that purpose. So we have to work on nonlinear map. And somehow it's kind of nature to see what would be the nonlinear map correspond to the modified linear operator. So of course there are many choices, but we just pick the simplest one. So we define this modified constraint operator. So here notation is a bit involved. Right? So here we are looking at really, say, fixed G and pi. And then this operator for any given initial data set, that will be just the usual constraint map plus this term. And we really care about just when gamma and tau are very close to G and pi. So if you do linearization at G and pi, that would just be the modified linear operator A we talk about. So once we work on this one, you can also see analytically it's really the same, has same properties as the usual constraint map. And then we can see somehow remember for the usual constraint map is the kernel of a joint property is trivial, then you have a subjectivity theorem, right? So we have analogous thing here. So suppose the modified operator, the linearization, a joint of linearization is trivial, then we have local subjectivity in this sense, right? Compact is supporting prescribing function, and then we have realized by compact is supported deformation. And moreover, that will bring up the dominant edge condition by this amount. C, the one we specify in this mu component. So which is good for some application is if you want to, say, find out condition where you can bring up the dominant edge condition. But unfortunately, this is not good for our gluing application. So there's a sort of gluing thing. If we want to do everything to infinity, and the scaling of those quantities are very somehow they competing with each other. So here is also just a heuristic feature. It doesn't help the proof, but you just see what the problem could be if you solely rely on C to bring up the dominant edge condition. So here is the one we want to bring inside the light cone, and now we have a mechanism. We know we can control the prescribing the position of the vector and the size of the light cone well by the modified operator. But if you just purely prescribe C, that means you change the mu coordinate, right? Keep J unchanged. that means you do lift, bring, lift up. So what could be problem is, for example, this deformation has to be very, very large. Somehow it's too large, it actually becomes competing with the leading order term of the constraint map, which related to mass. And so you should find the right prescribing thing to do. Somehow in this picture, probably you look shortest distance, but in reality, it doesn't have the shortest distance thing. So one thing we struggle a bit was struggling is to find out the correct prescribing for C and V, because we are not solving vacuum, right? Solving vacuum, you know what you need to solve. But here we are solving just inequality. So what would be the right quantity to work on? But as soon as we find out the answer, we find it's a very natural choice of the C and V. Okay? So I think I have a few minutes to talk about this subtle the subtle scaling thing. You will see in the proof. So, but then we have to work on further modifier operator. Because if we want to prescribe V, then that term will also add the first order change when you compute the norm of the quantity. So we add another term, which somehow is also to absorb the first order change. And then we have a strengthened result from previous result, previous list one. Oh, sorry. All right, so here we can bring up the C, but we don't change J. And now we, under the same condition, we can have the C to bring it out, and we can also eliminate any bad error term from J by prescribing V. But here we are looking at the same assumption, because we have a uniform estimate. Since we have a uniform estimate in this G, pi, and this V, as long as V is small, if this kernel is trivial, then for V is small, the kernel with this one, adjoint operator will also have trivial kernel. So it's also locally subjective. Okay. And then using that, we can do gluing. So given initial data set with E greater than P, the the time-like ADN mass and momentum. And then if we look at large ball, the radius R is very large, then we can keep in this big ball, we can find a deformed matrix such as coincide with the original G and pi in this big ball. And outside it will come from some model family, which we have some definition of the miscible family you can choose from. So of course, on the ball BR or outside the big ball, the dominant energy condition holds just by assumption. And so here we can choose a miscible family to be Kerr or Kerr-Newman. And the problem is over annulus. And we can also do that the annulus satisfy dominant energy condition. And in addition, we can also promote the ADN mass by bring up the dominant energy condition over an annulus. So there is a nice relation from bring up dominant energy condition and then bring up the ADN mass at infinity. Okay.
Questions?
Yes?
Because your epsilon, I mean, you would expect something which follows off to infinity, right? So epsilon is probably multiplied by.
Epsilon. Oh, right. So you mean more like a precise, like a
Yeah,
scaling.
well, you don't want to have constant energy at infinity, so you wouldn't guess it very good. So, well, maybe I'm confused with the regions, but
Constant
theta
energy.
is outside, right? So you don't want.
Right.
Okay, never mind. So maybe, I mean, it's not only E plus epsilon, but it's E plus epsilon times a function which falls off or something like that, right? Is it
But here is just constant, right? The E epsilon is just the E epsilon and P epsilon is just the ADN mass momentum of G epsilon.
Oh, I
right?
thought that was.
It's not mu, it's not
okay.
mu and Z,
Okay,
right?
fine.
So
Okay.
yeah, so the next slides I will tell you what really relation we have. Right? So here is just some picture we have. So here we have given G and pi, and then we can interpolate to some model family over this annulus region. And by the cutoff function, say chi is 1 there and chi we do localized deformation over this annulus region to bring up the dominant energy condition. And more precisely, this kind of tells you like what kind of Z and V we need to choose, right? The prescribing thing is that we actually choose that interpolate between these two data. So the one inside will be approach to the mu and J here, and toward the outer, the bigger sphere here will recover the AD, will recover mu and J of the model family, and then we bring up the bring up the AD mass. Okay.
There's no kernel condition here.
There's no kernel condition because we do as a vacuum thing. We use the miscible family, which can account for the possible kernel in the gluing procedure, right? So you can see actually the modified operator condition does not appear there, right? So that's just in the ingredients we use in the proof. Okay, so first we have to establish local subjectivity of this modified operator. But we already have some beautiful results from vacuum, from the usual constraint map. And here we are really just working with the one adding some zeros order term. So the same argument goes through. So we use the result Covalent-Shen and crucial delay for the usual constraint map. We more precisely follow Covalent-Shen's variational scheme to solve the equation, the linearized equation variationally. And then we adapt the norm from crucial delay, which is very effective local weighted norm that works very well to get elliptic estimate of the system using by Douglas-Nierenberg's elliptic estimate. And we're choosing, for aspirates, we're choosing exponential weights, so we can handle the smooth case as well. And one analytical improvement in all those procedures is we need to get uniform estimates in V, and also for other application, for matrix which very close to GM pi, right? In Covalent-Shen's result, they have a uniform estimate for the in the neighborhood flat data, but we have to, for other application, we want to do a neighborhood for arbitrary data. So we need to have some refined analysis on weighted subloop space for the L2 estimate, and then so in Covalent-Shen's work, they have some indirect estimate proved by contradiction, see what happens. But we have to have a direct argument there. So by looking at more carefully the weighted space under consideration. And then the scaling subtlety, I think we will run out of time, so I will leave that, but I'm happy to talk to anyone interested later. So there's scaling subtlety, and also it tells you, so here, one thing you may ask is like why we can bring up the ADN mass, right? We bring up dominant condition, but why can we bring up the ADN mass? The key idea is we are not solving really just the thing up to kernel. We can bring some element from the kernel, and we are solving that thing. And the thing from the kernel corresponds to a translation vector field, somehow help you to bring up the ADN mass. But I'm happy to talk to anyone interested after the talk. So some remarks is, so our work identify the paths which promote dominant energy condition and bring up ADN mass. But as in Justin's talk, I think what will be really interesting is see how can you bring down the ADN mass. I think there's some abstraction, or it is not so easy. So here is one thing I'm really interested to look at the decrease the ADN mass. And the other thing is to understand what will be the really honest abstraction from promoting the dominant energy condition. So remember, we are looking at the subjectivity, which is a stronger result, right? But even the subjectivity fail, can we really find a path to promote dominant energy condition? That's what we really need to apply. Danny and I have some partial results, and we're still working. I think it's very interesting to see what would be really the honest abstraction to do that. Let me stop there. Thank you.
Are there any questions or comments?
So the second point, what you're saying is that you have a trick to promote the thing, but maybe there is a real abstraction which lurks in there.
Let's tell you what our conjecture is. So we are really looking at the borderline case when mu equals J, right? So at least by conjecture, I don't know if Danny agrees. construction is being vacuum and killing initial data sets.
While you have this modified killing initial data or something like that. I mean, the
Right,
modified abstraction.
Somehow, I don't think that's something. The modified thing is I don't think it corresponds to something physical. But
they're probably unreal. That's what.
Unreal, right? So really, the true abstraction will from the space-time symmetry in the vacuum case. That's what I guess.
So when you change this energy condition with the muon term, you may create black hole. You know whether it creates or not.
So here, you mean for the gluing thing?
Well, no. In each procedure, you
Right.
do.
So for each procedure,
You may suddenly create black hole. Originally, there's no black hole, and then you may suddenly create black hole.
right. So now, because we are looking at small deformation, right? So for small deformation, as long as it's small enough, you don't create. But I think it would be interesting to see.
Black hole can suddenly appear. Minimal survey can suddenly appear.
Then I don't know. Yeah, that's a good thing to look at.
I think it's important to keep track of it. Otherwise, black hole and this condition are linked together. Well, after all, mu minus j, the condition that I deal with, mu minus j bigger than some diameter, black hole forms. So when you increase mu minus j, you may go above some threshold and then black hole forms.
Right. Okay.
So I think it's important to keep track of how black hole may be changed.
Right. Yeah. That's good.
Are there any further questions? If not, let's thank Lan-Hsuan again.
Could you go back a couple of slides?